Hi, my name is B Stout, and on behalf of all of the authors, I'd like to thank you for watching this video abstract, where we study the use of resonance states to describe the response functions of open optical systems. The techniques we develop here should be useful in a wide variety of physical systems, ranging from acoustics to colliding black holes. I'd also like to thank the French and Australian International Laboratory for financing this project. A response function is actually an operator that acts on arbitrary source currents or fields to generate the fields produced in response to these source excitations. Depending on the context, the response functions are constructed to produce either the total observed field or the scattered fields, and the respective response functions are frequently called Green's functions or T matrices. Although many computer codes and theories nowadays solve electromagnetic response to a pre-specified incident field or current source, response functions are more powerful, since they generate solutions for any and all possible excitations. This makes response functions very useful, but also notoriously difficult to construct, and this is a major goal of the research reported in this article. Resonance states are eigenstates of the field equations satisfying outgoing boundary conditions that we can then use to describe wave scattering and emission by the system. Light scattering by a single dielectric sphere is one of the simplest examples one can solve using resonance states. In this example, resonance states generally describe light that is temporarily trapped in an effective potential well near the surface of the particle. Light will then tunnel through this potential barrier over time and proceed to radiate into the outside world. A consequence of describing such decay processes by a wave function is that resonance state eigenfrequencies omega alpha are complex valued, with negative imaginary parts governing the exponential decay rate. A major mathematical difficulty is that exponential decay in time is necessarily accompanied by exponential divergence in space when one looks far away from the system. This difficulty was discussed long ago by George Gamow when he used resonance states to describe alpha decay. This far-field divergence is sometimes called the exponential catastrophe, since it makes it appear that it would be impossible to define resonance state inner products as field products integrated over all space. A major result of this article was to show that Gaussian regularization allows a superficially ill-defined inner product to be evaluated analytically to yield definite finite values. In the top figure of this slide, the electric dipole cross-section of a dielectric sphere is plotted together with the positions of the resonance state eigenvalues in the complex plane. We readily see that the real parts of the resonance states are generally located near cross-section maxima. The bottom graphs plot the real and imaginary parts of the angle averages of the inner product integrals. The resonance state normalizations are determined by evaluating these integrals and then used to determine the residues of the spectral developments of the response functions as illustrated in the next and final slide. As an example of the methods and formulas derived in this work, we determined the spectral expansion residues and eigenvalues to high precisions and even included the crucial non-resident contributions for the case of spherical scatterers. One could expect that this would allow us to approximately reconstruct response functions by truncating the spectral expansions to a finite number of resonance states, the truncation parameter being Lmax. What we found instead was that truncated spectral expansions do not converge to the true response functions and that they even predict non-physical behaviors. This problem proved particularly acute when treating dispersive materials like a Drude-Lorentz model for gold, as illustrated here in our article. The crux of the problem is that truncated spectral expansions don't preserve the analytic structure of the Fourier response functions. We solved this problem by modifying the response function residues to take into account the finite truncation of the spectral expansion and thereby constrain the truncated response functions to have the same analytic properties as their ideal non-truncated counterparts. As seen in this graph, a corrected truncated expansion with a sufficiently high Lmax does indeed reproduce the exact response function predictions for electric dipole cross-sections of a Drude-Lorentz modeled gold sphere. We thank you for listening to our video abstract, and we hope that it allowed you to better understand our goals and motivations. We think that resonance states are a powerful and fascinating way to do physics. We hope to provide further details and applications in future publications.